MapReduce is a programming model for distributing and parallelizing a large computation over a cluster of machines. It was originally developed by the power duo of Google, Jeff Dean and Sanjay Ghemawat in 2004. MapReduce solves the problem of being able to process a lot of data in a reasonable amount of time by distributing the computation over many machines. The same task that would have taken days or weeks to complete on a single machine can complete within a few minutes when it's broken down and distributed to a cluster of 2,000 machines. On the high level, MapReduce does two things: execute map and reduce functions that the user defines. The map function takes in a key value pair. For example, the key can be the offset in a large text file, while the value is the contents associated with that offset. The map function processes the value based on the user's specification and returns a set of intermediate key value pairs. For the text file example, we could be counting the occurrence of each word in the text, so we return a set of key value pairs where the key is a word and the value is the occurrence in that piece of text. The reduce function takes in the intermediate key value pairs that share the same key and merges all of the values for it. For the same text file example, it could sum up all the occurrences of a word that share the same key from the intermediate key value pairs and then save the final result for that key. The user only defines the map and reduce functions, while MapReduce takes care of partitioning the input data, scheduling tasks across a cluster of machines, handling machine failures, and the communication between machines. These are abstracted from the user, but let's take a deeper look and see how it does all of that. First, in the user's program, the MapReduce library, which is the implementation of the model, splits the input into M chunks based on what the user specified. Then, it starts up copies of the program across all the machines in the cluster. One of the copies is special, the master. The rest are workers that the master will start assigning work to. The workers will be executing M map tasks and R reduce tasks. The worker node that gets assigned the map task takes in a single chunk of the input and passes it to the map function that the user defined. The map function will process that chunk and then produce the intermediate key value pairs. The key value pairs are first buffered in memory, but they are eventually persistent on the map worker's local disk, which is partitioned into R regions or files, one for each unique key that corresponds with the one reduced task. The R locations on the disk are passed back to the master, which is responsible for forwarding these locations to the reduce worker. The reduce worker will make RPC calls to the map workers and request the specific key value pairs for the reduce task from each map worker based on the location that the master forwarded to it. Once the reduce worker has all the key value pairs, it will pass them to the reduce function and append its output to the final result file that is globally available. When all map and reduce tasks are done, the MapReduce call in the user's program returns, and at that point the R output files, one from each reduce task, are available and can be combined into a single result file or used by another service. To orchestrate the execution of the map and reduce tasks, the master keeps several data structures. For each map and reduce task, the master stores the state and the identity of the worker machine. Since MapReduce tasks are distributed over a cluster of thousands of machines, machine failures are expected. To handle worker failures, the master will periodically ping each worker, and if no response is received after some time, it will mark the worker as failed. In this case, any in-progress map or reduced tasks on a failed worker will be marked as idle so they can be rescheduled on another worker. In addition to that, on a map worker's failure, completed map tasks will also be re-executed since the result of the map function is stored locally on the worker's disk, and on failure it will not be available for fetching by the reduce worker. Master failures, on the other hand, are unlikely since there is only a single master, and that's why MapReduce aborts the computation if the master fails and lets the user retry in that case. But if we do want to have the master fault tolerant as well, that can be achieved by having the master persist the state of all map and reduce tasks so that if it fails, a copy of the master can be spawned and continue from where the last master failed. In a large cluster, it's likely that there will also be stragglers in addition to healthy and failed workers. A straggler refers to a worker that is healthy, so it's not marked as a failed worker, so it receives tasks to execute, but is very slow in executing its tasks, so it delays the completion of the MapReduce computation. This can happen, for example, when a worker has a bad disk that causes frequent correctable errors that still enable the worker to perform I/O operations, but substantially slow it down. MapReduce handles stragglers by scheduling a backup execution of map and reduce tasks when MapReduce is close to completion. This way, the task will be marked as complete whenever either the primary or backup execution completes, and stragglers won't be impacting the execution time of the MapReduce computation as much. To optimally execute a MapReduce computation, the M and R tasks should be much larger than the number of machines in the cluster. This will improve dynamic load balancing so that the workload is evenly distributed and the worker machine's resources are fully utilized. This will also help with handling worker failures, since in that case the map tasks will be distributed across all the other worker machines. The MapReduce implementation and programming model in general are powerful because many computations can be expressed as MapReduce problems. Problems that can be broken down to map and reduce subproblems and execute in parallel on a large cluster of machines. While MapReduce was Google's proprietary software, Hadoop is the first project that open-sourced the MapReduce model, followed by other big data processing frameworks like Spark that process data in the MapReduce way. If you want a Notion cheat sheet for MapReduce, if you're preparing for system design interviews, or if you're interested in distributed systems in general, you can check out the link below. And with that said, thank you for watching.